So we know that most ionic compounds are crystalline solids. They're going to have a definite crystal structure. In your descriptions of the things that you looked at in the lab today, what struck you? They were all real. I think you could have said, white crystals for all of them. They were all white or colorless. They were all, either granular or cubey or blocky or, crystalline. The descriptions didn't vary a whole lot. There were none that had a real sharp odor that was noticeable in the dry form. And what I'll tell you is that some of them were ionic compounds. Some were not. So when we do, and we talked about this briefly, we'll do a lot more with this next chapter and you probably did this in physical science, doing some basic formula writing. When you have two ionic compounds, or when you have an ionic compound, the formula, like in molecular formulas, it's the actual number of each kind of atom in a molecule. There are no molecules in ionic compounds. So this is just a ratio. That's all it is a ratio. And it's so that they balance out to be neutral. And like I said, we'll do a lot more with that next chapter. We did the Lewis dot diagrams, for instance. We showed sodium versus the sodium ion. Once it's given up its electron. We showed chlorine and the chlorine ion, I believe. And then copying that, whoops. And moving that. And remember, we always have to have ions in a bracket. So we saw those. This is where we hadn't quite gotten to. So they form, ionic compounds form these, it's a lattice. It's like if you imagine three-dimensional chicken wire or hardware cloth. It's like an actual framework, like a scaffold. And at each juncture point, you've got an atom. And we talked a little bit about, cutie pie and best friend and the rush of two things that are attracted to one another racing towards one another. That's a lot of energy. Until they hit a point where suddenly they're repelled by one another and they're forced backwards, which is also energy. So the crystal lattice is a setup where these atoms are stationary at the point where they're balanced, where the positive and negative charges are attracting one another and the positive and positive charges aren't repelling one another. So it's this real delicate balancing point. It's kind of like a high wire act. They're perched at the point where all of that energy is minimized, and it's all delicately balanced. So it tends to evenly space the positive and negative charges, and we don't look at bond energy the same way we did for molecular compounds. We talked about double and triple bonds and how they have more energy. We don't have the same kind of bonds here. These are not things that are interlocking fingers. They're just standing shoulder to shoulder. Instead of holding hands, they're doing knuckles. I don't know what the metaphor is. But we have to calculate the energy that's contained in that substance differently. It still has embodied energy. It still has this potential chemical energy. So we talk about it as lattice energy. And I don't, for the confines of a Chem 1 class at the high school level, I don't expect you to know much more about lattice energy than that it's sort of the corollary of bond energy, but in ionic compounds. The book definition is the energy released when 1 mole of an ionic crystalline compound is formed from gaseous ions. So if you've got sodium existing as a gas, and we can do that. If you have sodium existing as a gas and you have chlorine gas and you mix them, you've got gaseous ions. When they come together in the air, they're going to actually form sodium chloride. And I can show you a video of this.